Okay, and welcome back to part 2, lecture 2 of electrochemistry. And this will be the final lecture of our second semester of general chemistry at University of Alaska Anchorage. So, congratulations. Moving right into it. This is one of the more interesting triads of relationships when it comes to evaluating spontaneity in chemistry. And it's something that we revisit in organic chemistry, and we strongly revisit it again in biochemistry. And what we're going to be looking at here is just all the different ways that we now have at our disposal which we can evaluate spontaneity of a reaction or favorability in a reaction and the different angles and approaches which we can take. So we have the standard reducing potential of the cell. We have delta G, and we have K. And all of these have been used in this semester to describe whether or not a reaction proceeds as written in a favorable fashion or is spontaneous. In the case of delta G, if delta G is negative, it's spontaneous. And if it's 0, it's at equilibrium. And if it's positive, it's non-spontaneous. Likewise, we've seen that if the equilibrium constant K is greater than 1, because K is determined by products over reactants, that is going to be spontaneous. And we just found out that for the reducing, the standard potential for the cell, if it's greater than 0, that it's going to be spontaneous. So, what this means is we have the ability to evaluate them independently in terms of spontaneity. However, we also have the ability to relate them to one another. And that's what we're looking at right over here on this triangle, where we have G related to K, related to E, related to G. And conveniently, we have equations which give us the ability to move between these into one step. Now, it's not unusual to not memorize the bottom equation that I just underlined, relating the potential of the cell to K directly. Most of the time, I'll admit, when I'm asked to do that, I go from the standard cell potential to delta G to K. I'm using these other equations because I just don't have the other one committed in memory. But which you can absolutely do, it just takes a little bit longer, but it's not really laborious. So whichever approach you take is reasonable. If you want to memorize all three and practice all three, I think that's a perfectly reasonable approach. And it's probably a little bit faster than the one I utilize. But the equation we want to introduce specifically relates the standard potential of the cell to delta G. And that's going to be our second bullet point that we're just looking at here. And this is delta G naught equals negative N times F times E naught cell. And in this particular case, N is the number of electrons, and F is Faraday's constant. So Faraday's constant is 96,485 coulombs per mole of electrons. So let's investigate this just a little bit. This is a bit of a derivation, but this is just a derivation of the preceding equation that I was just talking about. Double underline and triple underline it here. And it's just relating, because delta G is related to K, we can substitute an F E naught cell for delta G, and then we can rearrange to solve for E naught cell, or standard cell potential, and get a direct relationship between E naught cell and K. So this is something you could derive fairly easily on your own, or you can just do it in 2 steps and solve. But if you substitute R and F and 298.15 K for temperature, because it's under standard conditions, we have 3 just non-changing elements we can standardize here. We get 0.0592 volts divided by N times the log of K equals the standard reducing potential, or standard potential of the cell. So, for expedience sake, it's probably worth your time to commit this to memory for this exam. However, if you remember the other two, you can get into the solution fairly elegantly and without much fuss. So, just for fun, let's do a conceptual connection question here. A redox reaction has an equilibrium constant, where K equals 1.2 times 10 to the third, in which statement is true regarding delta G for the reaction and the standard potential of the cell for this reaction. Let's see, A. Well, what do we know from this? If K is large and positive, it's going to be spontaneous, right? So in this circumstance, we'd expect to see delta G to be negative, and we'd expect to see E naught cell to be positive. And so I would select C. That is the correct answer for this particular question. You should be able to move pretty freely between these terms when asked whether or not something is spontaneous. So, let's do a question. Let's do an example. Use the tabulated electrode potentials to calculate delta G naught for the reaction. Iodine in solid form plus 2-bromide in aqueous phase react to form as a product 2 equivalents of iodide, aqueous, plus bromine in liquid form. And the question is this reaction spontaneous? So what we're going to have to do is use the tabulated electrode potentials to get to this answer. So we're going to refer to the table 20.1 in the text, and that we're going to use to get the components to calculate the standard potential for the cell. And then we're going to use equation 20.3 to calculate delta G naught from the standard potential of the cell. So that's going to be our plan here. So the solution, we have to break everything apart. We're going to grab our oxidation half reaction at the anode and the reduction half reaction, which would be our cathode. And that's going to be 2 bromides react to form bromine plus 2 electrons, and iodine plus 2 electrons react to form 2 iodide. And we have standard potentials for each of these, with the first being 1.09 volts for our bromine and 0.54 volts for our iodine. And when we sum these, we see the electrons cancel, and the sum when we subtract the anode from the cathode is a negative 0.55 volts. Now, what we would do to calculate delta G is use the relationship delta G naught equals negative NF E naught cell. And what's important, N, number of electrons, is going to be the number of electrons transferred, which in this case is 2. We also have our Faraday's constant, 96,485 coulombs per mole of electrons transferred. And we have our E naught cell, which is negative 0.55 joules per coulomb. So this, when you just do the math, is 1.1 times 10 to the 5th joules. And this is a strong positive value, which means this reaction is not spontaneous under standard conditions, which you probably could have ascertained from the fact that the standard reduction for the cell is negative. So, which I actually just iterated here in the check, so that would be your common sense check. Now, what I'd recommend doing is doing the exact same process on this following question, for practice 20.6. So just pause here, take a moment, work the problem, see if you can come to a reasonable solution, see if the rationale makes sense, and then we can move on. And now that we've moved on, here we are to another example. So let's use the tabulated electrode potential to calculate K. So the first time we were doing G, let's look at K for the oxidation of copper by free protons at 25 degrees Celsius, so under standard temperature. In this case, the reaction is solid copper plus 2 equivalents of protons in aqueous phase react to form copper-2 cations that are aqueous and an equivalent of hydrogen gas. So we're given this particular reaction, and what we want to do is find K. And we're going to do it through using the standard reduction potentials, calculating the standard cell potential. So, first thing we got to do is break everything down in half reactions, balance them by mass and charge, resum them, and in doing so, sum our potentials. So, copper at our anode is being oxidized. It is going to be solid copper going to our copper-2 cation plus 2 electrons. That's going to be our oxidation reaction because oxidation is lost. We are losing electrons from the copper as part of the reaction. And its standard reducing potential is 0.34 volts. And if we look at the reduction half reaction at the cathode, where we're gaining electrons, we're going to see 2 protons in aqueous phase receiving 2 electrons to form hydrogen gas, and this is our standard hydrogen electrode of 0.00 volts. And when we put these together, the 2 electrons cancel, we get a nice balanced equation, and when we subtract the anode from the cathode, we get a cell of negative 0.34 volts. Now that we have a cell of negative 0.34 volts, we can go straight to our relationship between our standard potential for the cell, 2K, which we have given, and we can plug and chug. How many electrons are moved here? In this particular case, 2, so N is going to equal 2, because 2 electrons moved per mole of per equivalent. And what else do we have to plug in here? Nothing else that isn't given. So E naught cell is going to need negative 0.34 volts. N is going to 2 divided by 0.0592 volts. And that gives us a K value of 3.3 times 10 to the negative 12th, which is a very small number. So, does this make sense? The answer has no units, which makes sense because it's an equilibrium constant, and it's a very small equilibrium constant. Now remember, equilibrium constants are products over reactants. So this would indicate that the reaction lies far to the left of equilibrium, or far towards the reactant side, which would indicate non-spontaneity, which makes sense because, once again, the reduction, or the potential for the cell is negative in this case. So, having run through this example, go ahead and take the opportunity to run the following question. And once you're done with that, let's jump right back into this lecture. But please do take the opportunity, because this is a good way to slow the pace of new information and to make sure you just run through the rationale one time on your own, so that we can just ingrain the concept a little bit before we hit those homework problems. Wow, so what do we do under non-standard conditions? Great question. Well, under non-standard conditions, we're probably going to be looking at a variation where we're looking at Q instead of K. Makes sense. So, because we already have this relationship delta G for non-standard conditions equals delta G naught, which is our delta G for standard conditions, plus RTL and Q, we can neatly substitute that this term equals this term under standard conditions, because delta G equals negative NFE delta naught cell, and add the RTL and Q term. And then we can just isolate E cell on the left side of the equation by moving negative NF to divide by both sides. So this term has to get divided by NF. And then we can substitute for RT and F, and we can come to our new constant. So let me rearrange that. And so we have a new equation for non-standard conditions, where the potential of the cell under non-standard conditions is going to equal the potential of the cell under standard conditions minus this conversion factor of 0.0592 volts divided by n, number of electrons, times the log of Q. This is referred to as the Nernst equation, and it's a very useful equation for looking at cell potential under non-standard conditions. So, are you thinking, I have to know this? Yes, you will have to know this. And since we have to know it, let's run a problem with it. Let's determine the cell potential for an electrochemical cell based on the following two half reactions. The oxidation half reaction is copper, solid copper, reacts to form copper 2 cations in aqueous solution at 0.010 moles per liter plus 2 electrons. And the reduction half reaction is permanganate in aqueous phase at 2.0 moles per liter plus 4 equivalents of protons in aqueous phase at 1.0 moles per liter plus 3 electrons react to form MnO2 solid plus 2 equivalents of liquid water. So, what do we have here? We're given half reactions for redox reactions, and we have the concentrations of all the aqueous reactants and products. And we're going to need those because we're going to need to find Q in the same fashion that we would find K. So, we know that permanganate's concentration is 2 moles per liter, the concentration of free protons is 1 moles per liter, and the concentration of copper is 0.010 moles per liter. And now that we have this, I think we are set to jet. So, let's get this all together, balanced as it should be. So, the copper is going to be our oxidation at our anode, and it's going to have a reducing potential of 0.34 volts. And our permanganate is going to have a reducing potential which is our reduction side, at our cathode, is going to have a reducing potential of 1.68 volts. Now, to balance these, because we have 2 electrons on the oxidation side and 3 electrons on the reduction side, we're going to have to take everything to 6 electrons so that we can cancel, right? So we're going to multiply everything by 3 up top and 2 on the bottom, and then we can cancel our electrons, and we're going to end up with 3 coppers, 2 permanganates, 8 protons on our reactant side, and then we're going to have 3 copper 2s on our products, 2 MnO2s, and 4 waters. And when we subtract the anode from the cathode potentials, we're going to end up with 1.34 volts. So now that we have this balanced redox equation, and we have E naught cell of 1.34 volts, what do we need to do next? Well, we need to calculate the the potential of the cell under non-standard conditions from given the standard conditions for the cell and the set of non-standard conditions that it's in. So, let's go right to our equation. We have E naught cell. We know what N is. It's 6 because it's 3 times 2. We had to get everything to 6 to make this balanced. And what's Q going to be? Well, notice we have a bunch of factors that we have to use for Q. But we also have some solids and some liquids which are excluded. So this is always reactants over products, remember. Our products, the solid doesn't participate, the liquid doesn't participate. Our only product that matters in terms of Q is our aqueous phase, for this example, and it's going to be the copper 2 cation. And we're going to have to raise it to an exponent of 3, which we see right here. On the reactant side, which is on the denominator, we have solid copper, which doesn't participate in the equilibrium process, and we have two different components in aqueous phase, the permanganate and the protons, and we have to raise them to their respective powers as well. We have to square the permanganate and we have to raise the protons to the 8th power. So now that we have this plugged in for log of Q, we're set to go. And we can just plug in 1.34 volts for our E0 cell. We have our standard number of volts that we're using, 0.0592 volts, divided by 6 for N, as our number of electrons that are being transferred in a balanced reaction, times the log of all of these bits. And when we plug and chug all this in together, we're going to get an adjusted voltage of 1.41 volts for this reaction under the non-standard conditions that are given, which is more potential than we would have had under standard conditions. So, under these conditions, the reaction does have a greater tendency to proceed towards products because of the greater cell potential. Pretty slick. Now, what I'm going to ask you guys to do, and I know I'm doing this over and over and over again, but it's really worthwhile, pause the video and try to run the exact same process for this following example here. Take a minute, run through it, validate all the things that you were just thinking about. And then once you've gone through it once, then we can proceed. So, driving non-spontaneous reactions. This is a really neat change of events in the way we can see electrochemistry. Because in all cells, whether they're voltaic cells or electrolytic cells, oxidation is going to occur at the anode and reduction is going to occur at the cathode. However, in voltaic cells, spontaneous reactions create electricity because the electrons want to move spontaneously from source to sink. They want to go from the reduced agent, which is, the oxidized reagent, which is losing electrons, to the reduced agent, which is gaining the electrons. And in this particular case, the anode is the source of electrons, and you're going to have the negative charge there, and the cathode is going to be accepting those electrons, and it's going to have a positive charge. Now, what if you have a non-spontaneous reaction? Well, the electrons aren't going to want to flow. But what if you apply charge across that system and drive electrons non-spontaneously? Well, that would be what an electrolytic cell is. In an electrolytic cell, you take a non-spontaneous reaction and you drive it through applying an external electrical current. And that's what electrolysis is. You take a non-spontaneous process and you make it happen by giving it the impetus to do so by applying electrical charge. So, this is the formal definition of hydrolysis, the process of using electrical current to drive any non-spontaneous reaction, and is carried out in an electrolytic cell. So it's just like what we were looking at before, but instead of receiving current, we're applying current. And when we typically think of electrolysis, it's not uncommon for us to look at the generation of hydrogen gas as our electrolytic process, or oxygen gas, through the electrolysis of water, which we're looking at here as this example. So let's compare and contrast once before we move on. Remember, for the voltaic cell, here we have a zinc copper cell. On the left, voltaic cell, and we see that we have our anode with our negative charge and our cathode with our positive charge, and the electrons are going to be removed from the zinc, flow through here. You can see that we have a net difference in potential of 1.1 volts, and then it runs down to the copper and is given to the copper, where it is applied to the copper 2 and precipitates solid copper onto the cathode. In the electrolytic cell, we have a non-spontaneous process where we apply voltage in the other direction. And you can see, because we're applying the voltage against spontaneity, the anode is on the opposite side and the cathode is on the opposite side. So as where the cathode was positive and the anode was negative for voltaic cells, note that the anode is going to be on the positive side of the battery, and the cathode is going to be on the negative side of the battery for the electrolytic cell. So let's dive into this a little bit more. So, in electrolytic cells, electrons are going to be drawn away from the anode, which has to be connected to the positive terminal of the external power source or battery. And electrons are going to be forced to the cathode, which must be connected to the negative terminal of the power source or battery. And the reaction that takes place is going to be non-spontaneous, but we're going to be motivating it through this applied voltage. So a spontaneous process would be the combustion of hydrogen gas in oxygen to form water. But in electrolysis, we could apply current to water and split it non-spontaneously back into hydrogen gas and oxygen gas components. Typically, the electrical energy is going to be supplied by direct current power, DC power supply, and sometimes electrolysis reactions require a little more voltage than the cell potential would predict, and this is called overvoltage. So for pure compounds, if you're going to undergo electrolysis of pure compounds, the compound has to be in a molten/liquid state. Typically, electrodes are going to be graphite. And in this particular scenario, cations are going to be reduced, and the anions are going to be oxidized. So does that make sense? Let's think through it real fast. Reduction is gain, right, of electrons. And cations want to gain electrons to become neutral. So that makes sense. And the anions are negatively charged. So to go to neutral, they're going to need to lose electrons. Oxidation is loss of electron. So that also makes sense. So let's look at an example. The electrolysis of liquid sodium chloride. So this is a molten salt. To melt salt, you have to get it super hot, by the way. In the electrolysis of pure molten salt, the anion, in this particular case, is going to be oxidized, and the cation is going to be reduced. So let's take a look at these two half reactions. On the left side, we have two chlorides in liquid form are going to react by giving up two electrons to form chlorine gas. And on the right side, we're going to have two sodium cations receiving those two electrons to form sodium metal. So over here we have our anode on the left, and on the right we have our cathode. And we're going to be applying the voltage from the anode to the cathode. And both of our electrodes are going to be inert in this particular case. So what do we do for mixtures of ions? Well, when one or more cation is present, the cation that's easiest to reduce will be reduced first at the cathode. That makes sense, because in terms of potential, if something's easier to reduce, it's going to go first. And we can determine what that is by looking at the least negative or most positive standard reducing potential. What's easiest to reduce? It's the one with the most positive reducing potential when we're looking at our chart? Simple. When more than one anion is present, the anion that is easiest to oxidize is going to be oxidized first at the anode as well. So what we do for that is we look at our chart and we look for the one that has the most negative reducing potential, or slash most positive oxidizing potential. So let's look at an example of this. Evaluating electrolysis of aqueous solutions. Let's say we're evaluating possible cathode reactions, and we're interested in the reduction of cation to its metal form. We're also interested in the reduction of water to hydrogen gas, as shown below here, where water receives 2 electrons and is split into its hydroxide and hydrogen gas components. Well, and then on the opposite side of this, what are our possible anode reactions? We're looking at the oxidation of an anion to an element, and we're also interested in the oxidation of water to oxygen gas, as we see below here. Let me go back. Which of these two has the greatest potential for the first part to be reduced? We have a reducing potential of negative 0.3 volts under standard conditions, and a reducing potential of negative 0.41 volts at a pH of 7. And we also have a reducing potential of negative 0.23 volts under standard conditions, and a equivalent negative reducing potential of 0.82 volts at pH of 7 for the oxidation process. So, oxidation of the electrode is going to be key, because graphite doesn't oxidize. Particularly, electrodes like copper will oxidize, but graphite's not going to oxidize. So we're going to have to go straight towards the half reaction that leads to our least negative cell potential, unless we get an overcharge. So here's a really nice example. We're going to be looking at this electrolysis of an aqueous solution where we have iodide being oxidized to iodine at the anode on the left side in blue, and on the right side water is going to be reduced to hydrogen gas at the cathode, and we're going to be facilitating this through the application of a voltage source across this system. So what are our two possible oxidations? Well, the first possible oxidation would be the oxidation of iodide, the 2 iodide anions, to iodine, I2, plus 2 electrons. And the potential for this as an oxidation reaction is negative 0.54 volts. Likewise, a possible oxidation would be water being oxidized to form oxygen gas plus 4 electrons plus 4 equivalents of protons. And the potential for this oxidation reaction is negative 0.82 volts. So, which of the two has a more negative potential? And in this particular case, the more negative potential would be, for the reduction anyway, would be the iodide. So, what we're going to be seeing here is this is going to be driven by the voltage source as part of our hydrolysis reaction. On the reduction side, possible oxidation, let's look at another one here. We've got our sodium iodide component, and Possible oxidations include the oxidation of sodium cation plus an electron to form metallic sodium. And this has a substantially negative cell potential, or potential of negative 0.271 volts. We also have two waters reacting with two electrons to form hydrogen gas plus two hydroxides, and this is going to have a potential of negative 0.41 volts. So reduction will be the one with the greatest potential, and in this particular case, the most positive version of that would be water, where the water is going to be accepting these electrons because reduction is gain, and two equivalents of water plus those two electrons is going to split those bonds between the hydrogens and the oxygens, forming our hydrogen gas plus two equivalents of hydroxide. So when we combine this into our overall reaction, you can see the hydrolysis drives the following overall reaction, where two iodide anions plus two waters react to form iodine plus hydrogen gas plus two equivalents of aqueous hydroxide. So let's transition here. We have 5 more slides and we are through the semester. So, stoichiometry of electrolysis. In any electrolytic cell, the amount of product made is going to be related to the number of electrons transferred. That makes sense because reactions require the bonds break and form, and that's regulated by the movement of electrons. So fundamentally here, we're going to be looking at electrons as a reactant. And the number of moles of electrons that flow through electrolytic cells depend on the current and the length of time. So if we go back to the very beginning of all of these slides, remember that 1 ampere equals a coulomb of charge per second, which a mole of electrons is 96,485 coulombs of charge, which is Faraday's constant. That said, I think we're equipped to do some prediction of products of electrolysis based on current that flows. So let's take a look at it here. I think this is super fun. I'm sorry, guys. I know this is everyone's cup of tea, but I love this stuff. So for this example problem, let's predict the half reaction occurring at the anode and the half reaction occurring at the cathode for electrolysis of each reaction. So A is a mixture of molten aluminum bromide and magnesium bromide, and B, an aqueous solution of lithium iodide. So let's start with A. In the electrolysis of molten salt, the anion is going to be oxidized and the cation is going to be reduced. However, this mixture contains 2 cations, right? So what we have to do is identify which of those 2 will go first based on its proclivity for reduction. So start by writing the possible oxidation and reduction half reactions, and then because bromide is the only anion, write the equation for its oxidation, which is going to be at the anode, and then at the cathode, both reduction of the aluminum 3 and the reduction of the magnesium 2 are possible. The one that actually occurs is going to be the one that occurs most easily, which is the one which is most reducible. Since the reduction of, in this case, aluminum 3 is going to be more positive in terms of electrode potential in aqueous solutions, that's going to be the ones reduced, and that's the one we're going to calculate. So, once again, we only have one anion, so we only have one oxidation going on. But in terms of reduction, it could be the aluminum, could be the magnesium, but when we look at the potential for the half reactions, we see that we have a more positive value for the aluminum 3, which means it's going to function, it's going to get reduced first. Because reduction is gain, it has a higher potential to gain those electrons, and it will accept them favorably faster than the magnesium does. And then B, since lithium iodide is an aqueous solution, there's 2 different oxidation half reactions possible at the anode. The oxidation of the iodide and the oxidation of water, because anytime we have aqueous, we have water as well. So what we have to do is we have to look at these half reactions and evaluate what could happen first. So we're going to write these half reactions for each, including their electrical potential. So remember to include the electrode potential of water, since it's under aqueous conditions, under standard conditions, and that's going to have a concentration of protons under normal conditions, because pH is going to seem to be neutral, of 10 times to the negative 7 moles per liter. So since the oxidation of iodide has more negative electrode potential in this particular case, it's the half reaction that's going to occur at the anode. Similarly, write half reactions for the two possible reduction half reactions that might occur at the cathode, and this would be the reduction of the lithium cation and the reduction of water. Under this particular set of circumstances, since the reduction of water has more positive electrode potential, it's going to be the one that reacts at the cathode. So, oxidation half reactions, reduction half reactions. We have for lithium iodide, possibility of iodide and water. Iodide has a potential of 0.54 volts, and water has potential of 0.82 volts when it's neutral. And because of this, the oxidation, remember, is going to favor what's lower on the chart. So it's going to favor the iodide. And for the reduction, we have the lithium and we have the water. And the lithium is very negative, negative 0.304 volts. And that means it's not going to be very good at getting reduced. And the water is negative 0.41 volts. And it's going to be favored. So that's a pretty easy solution. So let's take a look at another example here. We have a few more to go. So, this is fun. Gold can be plated out of solution containing gold-3 cations according to the following half reaction. So gold-3 in aqueous solutions plus 3 electrons can form solid gold. This would be electroplating. What mass of gold in grams is going to be plated by 25-minute flow of 5.5 amperes of current? And this sounds super scary at first, but if you just think of current as flow of electrons, and you know, based on Faraday's constant, how many electrons are flowing per amp, and you can then relate it to our stoichiometry of 3 to 1, we're going to be gold. Sorry, dad joke. So let's sort this all out. We know that there's 3 moles of electrons per mole of gold. We know we've got 5.5 amperes, and we know this is going to go on for 25 minutes, and we just need to find the number of grams of gold that are going to be electroplated here. So let's do it. Oh, this is a nice little conceptual plan. We need to find from our number of minutes, because we have 25 minutes, how many seconds is that? 60 seconds per minute. Then we'll have the number of seconds. Then we'll want to know how many coulombs, because 5.5 coulombs per second. Once we have coulombs, we can find the number of electrons moved, because it's 96,485 coulombs in a mole of electrons. And once we have the number of moles of electrons, we'll be able to divide by 3 to find the number of moles of gold. And then once we have the moles of gold, we can take the molecular weight of gold at 196.97 grams per mole, and we can find the grams. Whew! So let's do it. Oh wow, this is a very condensed solution. So, 25 minutes of charge at 5.5 amps is going to be times 60 seconds. Oh, they didn't break this out. I'm sorry, folks. Times 5.5 coulombs. Going through the whole rigmarole, I'm not going to talk all the way through it. It's going to be 5.6 grams of gold. So the important thing is, take the coulombs per second, identify the number of seconds, identify your number of coulombs from this relationship. Once you know your coulombs, find the number of electrons in moles with Faraday's constant. Once you know your number of moles of electrons, treat it just like any other stoichiometry problem you're comfortable with. Find your moles of gold. Once we know the moles of gold, go to grams per mole, and we are done. So, for practice, go ahead and take a look at silver here. So silver can be plated out of solution just like gold, and the question would be how much time in minutes does it take to plate 12 grams of silver using a current of 3 amps? Just use the same logical progression. Make sure you can work through this kind of problem. And you're done. You're done with General Chemistry 2, minus the final exam. So, congratulations. It's an enormous amount of material over the last 2 semesters. And I know this isn't everybody's cup of tea, but I hope everyone here learned a lot. And I hope that you developed an appreciation for the fundamentals of chemistry. And in particular, how this last chapter culminates a lot of the things that we've been talking about over the last year. So, that all said, take all these examples, go back into the homework, run those homework problems, get comfortable with the content. We're so close to the end of the semester. Let's finish strong. And I hope you all have a happy Thanksgiving week.